yeah. So today we're very happy to have Tong Chen, who actually currently is a postdoc at the Colin Broham's group at Johns Hopkins University. So I find his recent paper on the sort of signatures of a supersolid phase particularly interesting, even though it's still being refereed at the moment. And there's also a competing group paper. I see a lot of interest in this particular compound and its signatures for this so-called supersolid phase. So wanting to learn more about this. Yeah, so we invited Tong to give a talk on this topic. So you have like 40 minutes, 15 minutes to talk about roughly 30 minutes introduction, and then really sort of try to lay out your case for your work. Okay, Tong? Yeah, go ahead.
Yeah, so thank you for the introduction. I'm very happy to be here virtually. And today I'm going to talk about a little bit about our recent work on this interesting system, the potassium-2 cobalt selenium O3-2, and we'll call this K2Co. So the talk will be divided into 3 different parts. And first, I will briefly introduce the concept of a supersolid, and also why we are looking for a supersolid in the spin system. And then we'll go to this specific material K2Co. I will describe some measurements that we are familiar with, the magnetic and thermodynamic properties, which can be measured in a local PPMS. And then from which we can get the phase diagram mapped out. And then we already know a lot about system. But with neutron scattering, we can have the spectroscopic evidence of the supersolid phase using neutron spectroscopy. And also with neutron scattering, we can precisely determine the spin Hamiltonian for this compound. So please ask questions as we go along. So first is a little bit about the concept of supersolid. Supersolid concept is the combination of the superfluid and the solid. Superfluid is itself is a very quantum concept because it breaks the U1 Gauss symmetry, and this has been observed in helium-3 and helium-4. And we are more familiar with so in the Landau's phase transition theory, it's associated with the U1 Gauss symmetry breaking. And we are more familiar with the solid, which just breaks the translational symmetry. And for supersolid, we say if the system breaks the U1 and the translational symmetry, and these two are separates all the parameters, and then we say the system enters a supersolid phase in this case. And the supersolid phase, the concept was introduced by theorists a couple of decades ago, but experimentally there are some claims in solid helium-4 around 2005 in a Penn State University group, but the same group did several further measurements, and they concluded that later that it's not a supersolid in this case. But recently, around 2016-17, there are some results in the ultra-cold atoms field, and they're observing some signatures of a supersolid, which is the coexistence of the superfluidity and solidity, and characterized by the breaking of the two symmetries. The reason we are looking for such a quantum state in spin system is because there is some numerical results before around 2005, and they explored the triangular-lattice of hardcore bosons with repulsive interactions, and this is the spin Hamiltonian. So within certain parameter region, they find that the ground state is a supersolid, which breaks the both U1 and the translational symmetry. And since we know that there exists an exact mapping between the spin half degree of freedom and the boson hardcore bosons, so through this exact mapping, we can just rewrite this studied Hamiltonian into the spin Hamiltonian. And then in this, so we're actually familiar with this spin Hamiltonian, it consists of the Ising term, and then we have a transverse exchange term. So, and similarly, in some parameter region, the ground state is numerically predicted to be a supersolid state that break the U1 and translational symmetry. And the ground state spin configuration might be like this. It's a 3 sublattice order. You have a set of 3 sublattices, A, B, and C, and magnetic unit cell is √3 by √3 increased, and you have 3 spins in the magnetic unit cells. So this might be the ground state. This is the ground state predicted by numerical methods for this spin Hamiltonian in the easy-axis parameter region. So for the spin half x-axis model on triangular lattice, and there are more numerical explorations done with this Hamiltonian, and then they also have a Zeeman term. The magnetic field is along the out-of-plane direction. And if you go back to the hardcore boson model, that is the chemical potential, you can tune the density of bosons. And then in this case, it's the magnetic field. We can just tune that easily with magnetic field. But these are numerical studies, which appears around 2014-15. Left-hand side is the cluster mean field, and right-hand side is the DMRG. So they're mostly they're consistent, and we can examine several points in the parameter space we are familiar with, like the Heisenberg term when you have J perpendicular equals to JZ, it's 1.0 here, and then in zero field, so the y-axis is the field and the x-axis is the J perpendicular over JZ. And if you have Heisenberg system on triangular lattice, the ground state is 120-degree ordered. When you apply magnetic field and you select a configuration like that, and when the field is large enough, you have this up-down state. So which is you have 3 sublattice order, and on sublattice A and C, say A and C, you have spin up, and on sublattice B, you have spin down. So that's in the up-down phase. And then when you further increase the magnetic field along the axis, you go to a high field state, high field supersolid state. And then finally, when the field is large enough, you have all the spins aligned by the magnetic field. It's the up or the field polarized state. So this is from the cluster mean field, but for the DMRG, the result is also consistent. So basically in this phase diagram, you have 2 supersolid phases. So the low field phase, here it's greenish one. And then the high field one, you have the very magnetic coplanar phase, it's called. And these 2, they both break the translational symmetry because you have 3 sublattice magnetic order. And then it's also not collinear magnetic order, so you have in-plane components that gives you the breaking of the U1. So for these 2 phases, they're supersolid phases in the numeric calculations. So that's basically the concept of the supersolid and the reason why it can be realized in the spin system. So next, our focus on the specific material, the K2Co. This is the crystal structure of the K2Co, and this was the single crystal was grown first by the Covers group at Princeton University, and I believe the compound actually exists in database for a while, but and that was reintroduced by Bob Covers group to the community as a quantum magnet. So this system consists of a triangular lattice plane, which is formed by cobalt 2+, which has 3 unpaired electrons. So in principle, it can be spin in the low spin state, spin half, or high spin state, spin 3 halves. So for different system, you can have different spin state, but so in principle, you can determine this system whether it's in a low spin state or the high spin state by calculating or measuring using Raman or inelastic neutron measuring the crystal field scheme. But for transition metals, you have too many lines, too many levels to measure. So basically, what people in practice do is to measure this specific heat capacity, and they integrate the entropy. If the entropy release from very low to very high temperature saturates to R log 2, and then the system is thought to be have the spin half degree of freedom. And if the entropy saturates to R log 4, and then the system is thought to be in the high spin state, you have spin 3.5 degree of freedom. So in this case, we have entropy release saturated to R log 2, so it's spin half degree of freedom. So basically, you can think about this K2Co system as one triangular layer of spin half degree of freedom. And within the position of the single crystal XRD, we do not find any disorder in the system, so it's fairly clean. It's just spin half triangular lattice. Kava's group also measured the susceptibility as a function of temperature. And when the magnetic field is applied along the z-axis, we see the susceptibility is much larger than the case for the magnetic field applied in the plane. And this indicates strong anisotropy of J perpendicular and JZ. So in this case, it's easy axis. And same thing can be seen in the magnetization measurement as a function of field. When you apply z-axis field, magnetization increase rapidly and goes into a so-called, we call it a plateau. And then, but when you apply magnetic field in plane, and we'll see it's just gradually, slowly increases. And this also indicates a strong anisotropy. So the system is fairly anisotropic in this case. So previously we have the phase diagram by the numerical methods, and it shows a up-down state, 3 sublattice magnetic order. So we're wondering if this system is also showing the one-set magnetization plateau, so which means that we just don't have large enough field to access the fully saturation moment. And this is exactly the case. We went to Los Alamos to do the pulse field magnetization measurements. And this is the measurement at 0.6 Kelvin. And we see an extensive one-third magnetization plateau. And then you have a rapid change around 20 Tesla, and the magnetization saturates. The interesting thing we found in this measurement is that the transition is actually there are 2 peaks. It's double peak structure might be indicating some extra phase in between, which is consistent with the numerical calculations that there exists a high field supersolid phase here. But we have temperature dependence of this measurement. We measure at a couple of different temperatures, but we could not track the trend of these 2 peaks, which might be because there are some magnetocaloric effects happening here when you change the field rapidly, and the temperature of your sample also changes. And that's a characteristic of a supersolid as well. So the way to conquer this is that we measure the magnetization again in the high field facility, but at Tallahassee, that has a DC magnetic field. We measure up to 30 Tesla. So as we can see, if the magnetic field is not large enough, and then we cool down the system, and then the magnetization will goes to 1.3, which is about 1/3 of the full magnetization, 3.9. And only when you have magnetic field large enough, you cool down the system, and that will goes to the saturate moment. So the system still has a trend to go to the 1/3 plateau phase like this. So this is the measurement in the DC magnetic field. So we don't have complications from the magnetochloric effect and so on. On the right-hand side, I plot here is the phase diagram, which is the dm dt versus temperature and magnetic field. It's directly from the data shown in the panel A. And as we can see, there's a extended up-up-down state here, corresponds to the 1/3 magnetization plateau phase. And then at high temperatures, you will have paramagnetic phase, and at high magnetic field, when you have large magnetic field along the axis, all the spins are polarized. And then you will have ferromagnetic or up phase.
Tong, I have a question. So
Yes.
why do you expect that the up and down to all up phase, you see the splitting in the functional magnetic field, in base temperature before it goes to all three up phase?
So you're asking why we have this
Yeah.
splitting? That's a good question. So if we do, so previously I showed measurements, which is in the pulse field. So it's along the field direction. We observe two peak structure. And here I did DMDT, which is along the temperature cut. If you do cuts like this, you also find two peaks. So which is indicating that you have two transitions, and there might be another phase here.
Oh, so it's not so is it actually a first order phase transition from
That's a
up and
very
down?
good question. So from the numerical methods, yes, it's a first order phase transition, and also from the measurement itself, you can see a rapid change in the magnetization when you cool down. That's also indicating that this lower boundary is the first order transition. It's very consistent with the numerical calculations.
Okay. But which phase induces this upper splitting is unclear at this point, right?
It should be from this transverse term. If you don't have transverse term, and then all you have is the up-up-down phase and the up-up phase.
Okay, thank you.
So yeah, that's a very good question. I will come back to this, but previously we say that this compound is fairly anisotropic from the susceptibility and the magnetization measurements. So here, so why we just why not eliminate this term and see how the system compares to a classical Ising model on triangular lattice. And this is actually well studied around 1950s by Wanya, and then people use some numerical methods in 70s and 80s to simulate the phase diagram like this. So these are different methods, but they're all consistent with each other. So what we can do is that we actually can turn this phase diagram and to overlap it with our measured phase diagram like this. Interestingly, we find that the phase diagram can be scaled by 8.6 Kelvin in temperature or 3.3 Tesla in field to fit the measured data. And from the KBT and times the 4, which is from spin half degree freedom, spin half, and then we can estimate the exchange about 3 eV from temperature, just using the KB times this 8.6. And then we can also convert this 3.3 Tesla scale to exchange using the GS mu B and times 4, which is again from spin half degree freedom, and we again have around around 3 eV. So 3 eV for JZ is the leading energy scale for this system, and it should be pretty precise, which is because the system is very close to the Ising limit. But this is just a estimation of the JZ, the leading exchange. And go back to the numerical calculations. This is the DMRG, and this is the cluster mean field, and they both show two supersolid phases. So the two double peak stretcher, no matter along the temperature cut or the field cut, indicates an extra high field supersolid phase, which is actually consistent with this green high field supersolid phase in the calculated phase diagram. And then by comparing the span of the supersolid phase and the up-down phase, so we know that the system should be very close to the Ising limit. And by just comparing the ratios between these two phases, and we know that JZ is 10 times larger than J perpendicular. So from this, we also have a estimation of the J perpendicular just by comparing the phase diagram with the calculated phase diagram at zero temperature. Okay, so here's a summary of the thermodynamic measurements we have on K2Co. So we don't know a lot about the solidity or superfluidity. There's no science of these. And we also don't know if they're independent order parameters. For the spin Hamiltonian, if we assume the spin Hamiltonian is the x-axis model-like, and then we will now have an estimation of J perpendicular and JZ. We might have some hints of the quantum state in zero field, like we don't see any transitions in the specific heat capacity, no sharp transitions, but two broad peaks. That might indicate some quantum things, but we're not sure. But we do have access to the high field supersolid phase, which is predicted by the numerical calculations. So this is the measurements we are familiar with. Now we'll go to neutron scattering part. So neutron scattering is a very powerful technique in detecting these quantum fluctuations and find some details of the systems and yeah. Do you have any questions about the thermodynamic measurements or?
Oh, this is fine. Yeah.
Yeah, so again, the system is proposed by numerical studies, theoretical studies to be a supersolid. The ground state for this model in the z-axis region. And so what are we looking for? What we are expecting from neutron scattering? So from the system itself, the translational symmetry corresponds to the solidity. We'll see the modulation of the SC component. So you have sublattice order, and then you have SCs on different SCs on different sublattices, and then we'll say the system breaks the translational symmetry. And then for the U1 spin rotational symmetry breaking, the system should develop some in-plane component. So for the magnetic ordering, I'm showing here, they are all three sublattice order, but they're all along the moment are all along the c-axis. So they do not break the U1 spin rotational symmetry, only if the system develops some in-plane component, like what I shown here, and the system will break the U1 and form the supersolid. So this is for the elastic part. For the elastic neutron scattering, we want to determine the SC flat modulations through the lattice, and also we want to identify the in-plane component. And for the inelastic neutron scattering, we will rely on this Goldstone theorem, which says that for spontaneous broken continuous symmetry, so there corresponds to some quasi-particle set of gapless, which means that you'll have a gapless mode if you break the continuous symmetry. So in this model, the only continuous symmetry here can be broken is the U1 spin rotational symmetry. So which means that what we are essentially looking for in the inelastic neutron scattering spectrum for the evidence of the U1 spin rotational symmetry breaking is a gapless signal like this.
So where do you expect this to happen, Tong? I mean, this is as a function of a field, right? You'd expect to happen in between this split phase. I mean,
that's a good question. So the split phase is the so-called we'll call it high field supersolid phase. So it's too high in magnetic field, and we cannot access to that with neutron scattering. So we're not sure, but basically it's also a supersolid that breaks the same two symmetries. So we are expecting everything's the same, which is the if you measure the elastic neutron scattering, you will see c-axis line component and also the in-plane components corresponds to the solidity and superfluidity. And then for the inelastic neutron scattering, I expect to see also the Goldstone mode, gapless Goldstone mode for the high field supersolid phase.
Let me. I still don't understand. I mean, so in this particular case, that let's talk about the neutron scattering part. Yeah, in this particular case, so you're expecting the transverse component of the spin fluctuations to be a superfluid-like, whereas translational on the Z component to be solid-like. Is that what you're claiming?
These are both static magnetic moment. So you're measuring the magnetic structure.
But this is without any field.
Without any field. So this is the zero field. So in this case, we're looking at zero field case, and in zero field there's also a supersolid phase.
Only in that particular, only in that particular exchange coupling regime, J divided by JZ.
Right. This is the easy axis region. So throughout the easy axis region, we always have the supersolid phase in zero field.
I see.
So neutron scattering can only access the low field supersolid phase in this case, and so everything of the supersolid we present will be in low field or zero field.
Okay.
But basically, for supersolids, that breaks these two symmetries, and what we are expecting for the high field supersolid phase should be the same. A gapless Goldstone mode, and also the static moment should have both z-axis and the in-plane components, right?
I see, but I don't. I mean, but you haven't even know the exchange coupling constant, right, in this particular compound. I mean, how do you know you're already in this particular phase?
From just by comparing the phase diagram, we already have a pretty good understanding. Not pretty good, but just we already have a lot of information about the spin Hamiltonian of this compound.
Oh, so this arrow, the star, where's your exchange coupling constant? Is in the regime of a star or this arrow?
Yeah, it's the star. So we can first determine the leading exchange by comparing the classical Ising model.
Okay.
And then the JZ is about 3 milletron volts. And then by comparing the ratio of this high field, so-called high field supersolid and the up-down phase, we can know that the system is here, very close to the Ising case, and JZ is about 11.4 times J perpendicular. So we now have both knowledge of JZ and J perpendicular.
Okay, thank you.
So the first measurement we did was on high spec at Oak Ridge National Lab. Here's the data, which is the elastic scattering in the 0 Tesla field and also 7 Tesla field along the z-axis. Originally, we studied the system as a quantum spin liquid candidate because in the specific heat capacity, we don't see a sharp peak, sharp transition. So we study it as a candidate for quantum spin liquid, but surprisingly, we find that there are 6 peaks here, which are at the K points of the triangular-lattice Brillouin zone. And these 6 peaks are very sharp in the plane, which means that the system actually develops a long-range magnetic ordering in the plane. And the sharp peaks at K points was also observed in 7 Tesla field and 7 Tesla field, which drives the system into the up-down state. And then we can look we are now looking at the outer plane component of this K point peak that actually has a rod-like characteristic, which means that the magnetism is not correlated across planes, and you have a triangular lattice of spin halves, and it just barely talks to its neighbors. The system is fairly 2D, which is reflected by this rod-like characters of the K point scattering. And this might be the proposed magnetic structure for this zero field supersolid case. And we don't have any evidence of the in-plane component for now. And but we do know that the system has this K point from where it is there at K points, and we know that the system forms a √3 by √3 magnetic unit cell, and you have 3 sublattice order. You have 3 spins in the magnetic unit cell. You have ABC sublattices, and we can figure out the magnetization along the moment along the A, which is pointing down, is 2.6 μB per cobalt. That's heavily reduced compared to 3.9 from the magnetization. So, which indicates, again, there's strong quantum fluctuations in the systems. Another thing that's actually surprised us a lot is that we don't have any magnetic scattering in the middle of this hexagon, and that's at the gamma points. So if you think about a triangular lattice, 3 sublattice order, and then if you have classical spins, Ising spins that can only pointing up or down, you have 3 spins in a unit cell, magnetic unit cell, you always have some net magnetization. So in one layer of triangular lattice that has long-range magnetic ordering, you always have some net magnetization, and which will give you some magnetic scattering at gamma points. But you did not see it in the data set. So this is another time indicates that the system has a way to cancel the c-axis moment from its quantum fluctuations. So it can either form, say, up half down, which add up to 0 along c-axis, or up down 0, which also vanishes for the net magnetization in the sublattice order. So that's another thing we find very surprising. And that's the measurement in zero field. So in the up-down field, when we have magnetic field push the system into the 1/3 magnetization plateau phase, again, we find the 2D characteristics of the K points scattering, their rod-like scattering. But this time we did observe the magnetic intensities at the gamma points. So this is the uniform magnetization of the system. And at the very beginning, we feel a little bit counterintuitive to see both 2D rod-like scattering at K and also 3D scattering at gamma points. But this is essentially the net magnetizations. It does not necessarily mean that the system is 3D correlated. So even in the up-down state, you have 7 Tesla applied, the system is long-range ordered, classical, incompressible up-down state. The system is still very two-dimensional, so the triangular lattice plane of spin halves still do not talk to its neighbors. And from the refinement, we know that the magnetization is 3.9 μB per cobalt, which is exactly the saturation moment, 3.9 μB per cobalt. So this means that we have very good knowledge of the up-down phase. And later we'll use the spin waves in the up-down phase to precisely determine the spin Hamiltonian. So as the in zero field, the system, the moment is heavily reduced, significantly smaller than the 3.9. So we will expect quantum fluctuations in zero field, low temperature. So that's that's the reason why we use inelastic neutron scattering to detect that. So the x-axis is the wave vector dependent, and the y-axis is the energy transfer. So in this case, we have some excitations forming kind of bands, flat bands at certain energies in the spectrum. And at the very beginning, we are also feel very surprising, which is because it does not show in any other systems, but it's actually very natural if your system is fairly close to the Ising limit. So if you think about the Ising system, you only have the JZ term, and each spin you want to flip it from, say, down to up in the middle, and the energy of flipping this spin is totally determined by the exchange field of its neighbors. So in this case, you have 3 red spins pointing up and 3 blue spins pointing down, so the exchange field cancels out, and then you have this quasi-elastic scattering by forming from flipping the middle down spin to up. And then because of the quantum fluctuations, and you might have spin configurations like flipping a center down spin to up with 4 up spin neighbors and 2 down spin neighbors. And in this case, you will have energy cost, which is Jz. And then similarly, if you have 5 spins up, 1 spin down neighbors, and then you will have to, it will cost you 2 Jz to flip the middle spin. So that's pretty natural for the spin systems. So in this case, we can just actually read out the leading exchange Jz in this case. So we find that the system has equidistant bands, and the gap is around 3 millielectron volts. That's exactly the Jz we estimated from previous comparison between the numerical method and measured phase diagram. So from inelastic neutron scattering, we can just read out the exchange couplings Jz like this. But for the ground state characteristics and also the supersolid we are interested in, so we must zoom in to these bands with better resolutions, and this is actually done on another instrument at Oak Ridge National Lab, which is the CNCS. So previous measurements I show you was measured with 9 millielectron volts, and now the EI incident energy is just 1.0, so we have much better resolution. On the left-hand side, I show you is actually the zoom in of the quasi-elastic bands in the previous measurement. So when we zoom in with the CNCS, we find that there's a sharp spin wave-like modes like this, and then you have broad continuums, which was bounded by the spin wave-like excitations. But I want to point out here that these sharp excitations, they're spin wave-like, but they're not actually spin waves, because so the ground state is actually a quantum fluctuating state. It's not the elementary excitations is not magnons or spin waves. So these are all given by the transverse term, the quantum fluctuations introduced by the transverse term J perpendicular in the spin Hamiltonian. And on the right-hand side, I showed the constant energy cuts. So you have 0.07, 0.13, and then it's like you increase the temperature and you have intensity stems out from K points. And then you also have intensities. So when you increase the cuts energy, the energy of the cuts, and then you at very low energies, you find K points, it stems out. And then at certain energies, about 0.1, you have the excitations from M points. M points excitation, it also stems out from M. And then at higher energies, you have diffusive scattering from all different contributions. So for me, it's like you have quantum fluctuations which select one of the order parameter, one of the wave vector to order, which is the K1 point, where we observed elastic scattering, the 6 points in the elastic scattering channel, and we associate with the root 3 by root 3 sublattice order. But you also have this kind of instability at M points, which are here. And if you change the scale, you will also see the peaks at stemming out from the K/2 half K points like this, and then that's are all rotational scattering or different instabilities that the system may order but does not order. So the system finally chooses to order at the K points.
So these are basically just spin waves, right? I mean, you're basically the spin waves coming from this. I mean, the elastic scattering you see, right?
Well, I don't think they're spin waves. So they're just very sharp excitations from the ground state, and the ground state is not a is you have quantum fluctuations from ground states, and you can compare to the up-down phase later, and you will see the ground state is the low energy excitation is actually contains a continuum of scattering. It's fairly broad, much broader than the spin waves.
I see.
So I want to first examine the Goldstone modes and Goldstone theorem. So we find this gapless mode, which might be the Goldstone mode indicating the U1 spin rotational symmetry breaking. But actually, the system can also have the pseudo-Goldstone mode, which is also may appear gapless, which is from the accidental degeneracy. But in this system, we know that the solidity part will lift this accidental degeneracy. So this mode is still gapped because of the six-fold anisotropy in this case. So still, we are expecting a gapless Goldstone mode. And then we are expecting a gapped pseudo-Goldstone mode, which is lift XY degeneracy. So at K points, we are actually expecting something like this. This is very consistent with our measurements with the lowest EI we use, which is 0.72 electron volts. We observe a peak at finite-energy, which might correspond to the pseudo-Goldstone mode, which is gapped. But system is still gapless at lowest temperature and lowest energy, which indicates that the system has broken U1 spin rotational symmetry. And that's the superfluidity part of the superfluid. I hope this experiment will convince you that at least this is some great data that shows that the ground state might be a supersolid because of just by the definition, it breaks the U1 and the translational symmetry. But the system is also very interesting as just a quantum magnet. So in this case, what I show here is the field dependence of the spin excitations at 2 Kelvin. And if you have 0 Tesla, that's that's measured with causal resolution and at slightly higher temperature. We saw that the spin excitations is very diffusive. But when we increase the magnetic field, we go deeper and deeper into the up-down phase. We find the spin wave excitations pop up. And it's fairly sharp, very, very sharp in both energy and the wave vector dependence. It's just well-defined spin wave excitations in this case.
But up and down has quite a few atoms per unit cell, right? Why do you only see one set of modes?
That's the low energy part, and that's also a not so good spaghetti plot. So I will show 3 different modes in the upper bound phase later.
Okay.
Basically, what happened here is that you have 2 modes, they're overlapping for a lot of wave vectors. So you have 2 modes here, and then at very high energy, about 9 millectron volts or 8 millectron volts, you have another band there. But Weir goes into that.
Okay.
So we not only observe the continuum of scattering becomes, they're forming sharp spin waves, but they're also moving up in energy when you increase magnetic field, go deeper and deeper into the upper down phase. So yeah, so this is a full spectrum of the spin waves, which is measured again by 9.0 millectron volts in 7 Tesla field along the z-axis. And we can, indeed, we have 3 different bands, which is because we have 3 sublattice unit cell. We have 3 moments in 1 magnetic unit cell, 3 spins. And then we should have 3 bands in the spin wave excitations. It's also simple to examine whether they're at the correct energies, because you can associate with the spin wave energies with the flipping spins. If you want to flip the majority rad spin up spins to down, its exchange field from its neighbors, you have 3 ups, 3 downs for rad spins. So the energy you have to spend is only the Zeeman term. So for this case, for 7 Tesla field, it's around 3 millectron volts. And for the downspins, you have 6 up neighbors, which gives you an exchange field. And also with the Zeeman field, you have about 6 millectron volts energy to flip this downspin to up, which is also consistent with our measure spectrum. So since this is a stable, incompressible order state, we can use linear spin wave calculations to simulate these excitations. If we have model like this, just x-axis model, and then we have a precise determination of the J perpendicular J and also JZ, and by minimizing the chi-square. But we can do more things with this. So if we add further longer interactions like J2Z and J2 perpendicular, we can show that it's very close to 0. So longer range interactions are insignificant in this compound. So this simple x-axis model really describe the system very well. So now I want to give a summary of the neutron scattering results. So neutron scattering did find the signature of solidity, which is in the elastic scattering you have 6 points at k points, and then these means that the system breaks the translational symmetry, and it is forming the 3 sublattice order. And then we also have the evidence of the superfluidity, which is the gapless gold-stem mode in the inelastic neutron scattering spectrum. And on top of that, we have the pseudo-gold-stem mode, which is gapped, and which is from the lifted XY degeneracy. And for neutron scattering, we can measure the temperature. We can have measurements at different temperatures, and we did the measurements, and we find that the temperatures at solidity and the superfluidity develop, they're happening at different temperatures which means that there might be independent order parameters which is required for the spin supersolid. And for the neutron scattering, we can precisely determine the spin Hamiltonian, and we can also set very tight limits for the next nearest neighbor interactions or c-axis interactions. So we prove that the system is well described by this x-axis model on triangular lattice. And then neutron scattering can also observe several signatures for the quantum state. So first, in the elastic channel, we find the gamma points vanishes for zero field, which is because you have strong quantum fluctuations, and the moment along c-axis should add up to zero and give no net magnetization. And this can only be done if you have say up half or up down zero states. So the these states cannot be classical up or down. And then in the inelastic channel, we have flat bands at 1 JZ, 0 JZ, quasi-elastic, and 1 JZ, 2 JZ. And we also have 3 JZ, which is observed at by terahertz. We have these flat bands indicating the quantum fluctuations in the system. But one of the limitations of the neutron scattering is that we don't have any access to the high field supersolid phase, unfortunately. And currently, we can easily go up to 14 Tesla doing neutron scattering, but we will require 20 Tesla to access the high field supersolid phase in this compound. So yeah, so the results are currently under review. And I want to thank the co-authors, collaborators in this project. At Johns Hopkins, we collaborate with Peter Armitage group to measure terahertz, which observe the 3 JZ flat bands in terahertz. And the neutron scattering experiments are done at Oak Ridge National Lab, and the inelastic neutron scattering we carry out 2 inelastic neutron scattering experiments on high-spec and CNCS, and 1 neutron diffraction experiment on HB3A. The materials was grown by Bob Cava's group at Princeton University, and then the high field magnetization measurement was done at MagLab, both at Los Alamos National Lab and also the Tallahassee MagLab. And I also want to thank the series that are not co-authors, but they do have very helpful constructive advices. So one is the Rice group, Xu Yi and the Andrew Navidonis group, and they use IPIPs to simulate the excitations of supersolid quite well, fit quite well with the experimental observations. And the other is the IOP group, Li Yuwei's group, and his graduate student Gao Yuan. They use the MRG method to simulate the spectrum. And recently, these are some preliminary results using supersolid magnetocaloric effect of the supersolids to cool down. And the serum rhodium arsenide is a heavy fermion superconductor that superconducts below 0.3 Kelvin in 0 Tesla. And by using a device based on the magnetocaloric effect of a supersolid, and they managed to build such a device to measure the superconducting transition in the resistivity versus temperature plot. And down to the lowest temperature they can reach is 25 millikelvin, and the system is helium free. So that's that might be one of the applications of the spin supersolids in the future.
Okay, thank you, Tong. Very nice result. So I wanted to ask you some other questions. I mean, so what do you expect to be the differences in the signatures for the low field and high field so-called supersolid phase?
Yeah, that's a good question. So for the supersolid phase, by definition, it has Goldstone mode. So I'm expecting a gapless mode for the high field supersolid. And Well, I mean, we have advanced numerical methods like what I just mentioned, IPEPs and also DMRG, and they can give fairly good calculations for both supersolids. So in principle, you can just collaborate with these groups to simulate the spectrum for you. But
Okay, yeah, Doc Nicholson has a question. Yeah, hello, Doc.
Hi, sorry, I was late because I was teaching. Um, this is very cool stuff. As you know, I'm very interested in, at some point trying to really do some other measurement techniques on this material. Could you say a few more words about why is there a large magnetocaloric effect? I think I just missed that. Because that's pretty intriguing that you can do what I guess must be the analog of demag cooling with this stuff and do so well. What's the physical origin of the magnetocaloric effect here?
um, in this case, so the origin of the magnetocaloric effect is from the low energy excitations. So if you have a system that has a gapless mode, a lot of excitations at low energies, and in principle you can use it for magneto cooling. In this case,
Okay.
you don't need it does not. It means that supersolid is one of the candidates that you can use to do the cooling, but not the only magnetic systems to.
I mean, certainly you can have a paramagnetic salt or something like that. But I guess and obviously people do nuclear demagnetization, but I guess with the paramagnetic salts, I guess usually the issue is that um, the exchange, basically the excitations are gapped. And so there's a lower limit to how cold you can get. And I guess the point here is that you have effectively gapless excitations, right?
Right, you have broken U1 and then you have gapless low energy excitations for the cooling applications.
Okay.
Yeah,
Yeah,
I don't completely
I'm
understand.
struggling a little bit with why everything that has, well, yeah, why everything with magnons isn't in principle able to do this. But I guess the point is almost everything ends up having gaps.
Yes, you're exactly right, because as you can see, the system has very large anisotropy.
Yeah.
And for systems that is sad anisotropic, you still have gapless excitations. So itself is very exotic.
Okay. Thank you.
So what do you expect to happen in this case if it's up and down to the all up states? You expect this gapless excitation to disappear?
For the up down state, you still have a gap. So let me go to the spin wave excitations.
Yeah, so your zero energy mode that you see in the previous slide, right?
So in principle, you have two branches going up as spin waves when you increase magnetic field, and you also have one branch moving down in energy when you further increase the magnetic field. So in the high field supersolid phase, the upper band will goes down to quasi-elastic energy region, and then it will form some gapless mode as required for the U1 spin rotational symmetry break. That's what I expect for the high field.
I see. So then I mean in this plateau of up and down phase, you should expect to see the energy coming down of the 6 millivolt, whatever the 6 millivolt mode, and then the other one goes up.
Yeah. So as we can see from the previous slides, so if you increase the magnetic field and then the two dispersive modes moving up and the one at higher fields should move down.
Okay. It's
Because
continuously moving down?
yeah, will move down because you can also understand with the flipping the up spins or down spins.
Okay. Very interesting. Yeah. Are there any other questions for Tong from the audience? Yeah, I need to understand more. I mean, I don't completely understand what you're talking about yet, but yeah, okay. Yes, thank you, Tong. Yeah.